first hour to introduce you to plane wave. Okay, the plane wave and plane wave propagating in an unbounded lossless media. And then in the second hours, okay, we will do another quick revisions of the previous 3 chapters. 1, 2, 3, previous 3 chapters once again. Okay, so to get you ready for this Friday's quiz. Okay, this Friday's quiz is in LT6, right? If I'm not wrong. Okay, in LT6, please be there punctually, because we'll give you 10 minutes to get settled down, and the test will start at 4:10. All right, and it's going to last an hour. Okay, you will submit at 5:10. All right, that will be the last test. The quiz. All right, plane wave propagation in lossless media. Now, in these chapters, in the beginning of this chapter, you will see a lot of equations. Okay, the equations are basically for basic understanding to arriving at the results. Okay, the important thing is how to make use of the results. Alright, we are not expecting you to do all the derivations in this chapter or in the previous chapter. Okay, just like we don't expect you to know the derivations of the divergence theorems or the derivations of the Stokes theorem. But you have to know how to apply the divergence theorem and apply the Stokes theorem and apply the plane wave propagations in solving problems. Okay, but then somebody might want to ask, in that case, why are you, doing all these derivations and all these things? Now, it is not right for us to just give you a law and then say that you apply without telling you why. Okay, if I just tell you, say this is the Gauss law, you apply it without telling you what is the physical meanings and what is the, how does it come from, it does not seem right. Okay, remember, just like when you are very young kids, primary school, if I tell you times table, 3 times 4, 12, 4 times 4, 16. Okay, and then you just memorize, commit the memory, and then just recite it. Without telling you that 3 times 4 is actually, you add 4 3 times, or add 3 4 times, so you arrive at 12. Then you just commit 3 times 4, 4 times 4, 16, 5 times 4, 20. And that is not the right things to do, broad learning. And that's the reason why we are going to explain to you, okay, what Helmholtz equation is all about, how does it comes about. But at the end of it, and I think at the end of the lecture, I will summarize basically what are the takeaway, okay, what are the things that you need to know, all right? So you don't have to say, wow, I have to learn on so many equations. Okay, now first set of equations is already scared a lot of people out already. Now, this is the so-called Maxwell equations, the 4 out of the 5 Maxwell equations. Remember, the 5th Maxwell equation is actually the Kirchhoff current law. Okay, you have your Faraday's law, you have Ampere's law, you have Gauss' law for electric charge, you have Gauss' law for magnetic charge. Okay, this is so-called the integral form, and this is called the differential form. Now, do you remember this one? Faraday's law, EMF is equal to minus d phi dt. Remember this one? And phi is equal to integral of b dot ds. Remember this one? Okay, so this is actually your EMF. Okay, and your EMF is equal to minus of E dot dl, remember? EMF equal minus. So this is your Faraday's law, together with the definitions of potential or relationship between potential and electric field. And this is your Ampere's law, obviously. Okay, integrations of H dot dl is equal to I, and plus I equal to current density integrated over the surface. Okay, so this is obviously Faraday's law, Ampere's law, Gauss' law, the 2 Gauss' law for electric charge and for magnetic charge. There is no such thing as magnetic charge, and therefore this is the right hand side is 0. Now, this is for electrostatic, okay, and electromagnetic. Sorry, electrostatic and magnetostatic. Alright? Now, but what happens if there's a time varying field when the charge, okay, is not constant in respect to time, but changing in respect to time? The Maxwell equation got modified by adding one terms here, del D, del T here, del B, del T here, because now the current will have two folds. The current will have two components. One component is what we call the conduction current, and one component is what we call the displacement current. Okay, and the displacement current density, this is our conduction current density and displacement current density. The displacement current density is what we call the del D, del T. Okay, the rate of change of electric flux density with respect to time. Alright, now what does it comes about? We briefly mentioned it previously. We say that, well, there's one of the simplest reasoning, or say simplest example, analogy, is looking at a capacitor. Okay, you look at the capacitors, you say that I'm charging the capacitor. No current in, current out. Now, isn't it look funny? Because basically, there are two things here which should cause you to wonder. First thing first, if I take this as a node in your KCL, very easy, right? The sum of current that go into the node is equal to 0. Right? One in, one out, so the sum is equal to 0. But what happens if I take the node as here? Okay, KCL fails because current going in, there's no current going out. Or I take a node here, KCL also fails. There's current going out and no current comes in. Cannot be. Okay, so that means there is some kind of current still flowing in between. Okay, some kind of current that is still flowing that you cannot measure using your ammeter. Okay, so what is this current? This is our so-called displacement current. And another way to looking at it, to say that, well, again, we mentioned it before, because of a current, there's magnetic field here, there's magnetic field here, so you plot the magnetic field, it is like this, and it is like this, and can it be suddenly 0? It cannot be. So though the magnetic field must be continuous, if it's continuous, where does this magnetic field come from? The magnetic field must come from current, because according to Ampere's law, magnetic field is always generated by current. Alright? Because when you do this H dot dl, it must be equal to current enclosed. So if I do a H dot dl around there, I find magnetic field, there must be current. Okay, so this is the way to think it. Now this slides here, it should shows that, okay, actually the current inside, or the current flowing into the capacitor, is the same as the current inside the capacitor. This is what we call the conduction current. This is what we call the displacement current. Okay, let's look at an example here. Let's say apply a voltage Vs. Okay, apply a voltage Vs, which is equal to V naught cosine omega t across the capacitor. Okay, apply a voltage across the capacitor. Then the current that is flowing into the capacitor, I1C, the current flowing into the capacitor, I is equal to C dV dt. Alright, this is what you have learned previously. So the current the physical current that flow is equal to I equal to C dV dt. So you differentiate dV dt, this is the current that flowing into the capacitor. Now, on the other hand, if you apply a voltage across the capacitor plate, you will get electric field. Alright? So the electric field E is equal to P over D. This is what we get. Alright? Now, let's assume that I'm correct. I have a displacement current density which is equal to dV dt. let's assume that this is correct. Assume that it's correct first, alright? Okay, then my J equal to dt. But what is D? D is equal to epsilon E. Remember, flux density equal to epsilon E, so I put the epsilon E here. I differentiate this E, and this is my J. Alright, so this is my J, this is my current density. Then the total current is I is equal to J times A. If I equal to J times A, you can multiply in here, and you can see that what is this? Epsilon A over D. This is your capacitor. Okay, this is a capacitor of a parallel plate capacitor, so equal to C dV. So you can see that exactly the same. The so-called conduction current flowing into the capacitor is exactly the same as the displacement current in the capacitor due to this changing of electric flux. Alright, so an intuition can be shown to be correct. Okay? So this is, but you don't really need to know what, I mean, not really to know. You should know all this, but we are not going to ask you to prove all this. Not to worry. Now, okay, so this is, once again, just a summary, okay, of the electrostatic when del D del T equal to 0. That is in the first slide. Okay, this slide is once again replace this slide. So this is what you have learned previously. Okay, from now on, we are going to switch to this one now. Okay, we're going to switch to this one. Now, but we are not going to be so nasty lah, huh? Okay. Maxwell equations, okay, is known to be able, open and close inverted comma, solve any electromagnetic problems in the world. Okay, but in reality, okay, theoretically it can be done. In reality, it is very, very difficult to use. Okay, so what people have done is people manipulate the Maxwell equation, manipulates the 5 Maxwell equation, a set of equations which can be applied to a specific applications. Okay, just like those economic theory, I mean, they are economic theory that's supposed to say that they can solve all the problem of poverty and all this in the world, but you know, they always have to go and find a tweak here, tweak there, tweak here in order to make sure it works, right? Okay, so this is once again the Maxwell equations. Now, why does it look so different from this one? This is what we're supposed to start from here. Okay, we're supposed to. What's different from this one? Now, the difference is that, okay, we say that we are going to be interested in propagation in free space, and in free space there's no current flow, no conduction current flow. In free space, how can there's no wire? Where's the conduction current flow? So J goes to E0, and free space there is no charge. Rho go to 0, and we are not going to work with D or B. We are going to work with E and H. So D is equal to epsilon T, and B is equal to mu H, and we sub this on in here. Okay, and alright, we sub this curl of E now become curl of E equal to minus del D del T, curl of H equal to del D del T, and this one becomes sub this one inside here. So this is what we have. Okay. Curl of E, remember, we have the first one is curl of E is equal to minus del D del T, so it becomes minus del mu del H del T. Okay. Then the next one we got curl of H is equal to del D del T now become epsilon del E del T. Okay, and then divergence of D become epsilon divergence of D. Okay, so this is just, you don't need to memorize all this. All right. So this is become our new sets of Maxwell equations, and not yet. Okay, the manipulations means that we have to find the curve, find the curve of left hand side and right hand side. We find the curve of left hand side and right hand side. Okay, and then we substitute backward. Okay, we find the curve of left hand side and right hand side. Let me see here. Let's write down here. You see, I have curve of E is equal to minus mu del H del T. I have to write all this. So if I find curve of E is now equal to minus mu del curve of H del T. Alright? And I sub the curve of H inside here. I sub the curve of H inside here. Okay, I sub the curve of H inside here. Then becomes something like that. That's the differential equation. Okay, so at the end of it, that is my so-called wave equations for electric field. And same thing that if I find curve of these equations, okay, and do some manipulations, I will end up with these equations. Okay, so these are the so-called wave equations for electric field and magnetic field. And these are the equations that we will use to solve our wave propagations problem and not the Maxwell equations problem. Okay, this is what we have here. And remember, what is the del squared? The del squared is the so-called Laplacian, remember? Alright. Now, but these equations are still look quite complicated. So what are we going to do next? We are going to simplify the matter even further. Okay, first thing first. I say that my electric field E supposed to be a vector. It's a function of positions and it is a function of frequency. Alright? So can I say that now E is equal to a function of positions and E j omega t. That means my electric field is a sinusoid. Okay, this is a phasor form you learned before, right, in the first year. Okay, so if it's a sinusoid, it is a simple form and it is a sinusoid. So what are we going to get? Okay, this one first, we'll come back. Okay. If I substitute now E, okay, as a sinusoid inside here, then what do I get here? I differentiate with respect to t twice. Del E del t is equal to del E R E j omega t dt is equal to j omega E R. Right? Remember? This is the only part that has the time variation. So you differentiate this, you get j omega, and you get this one, E j omega t. Remember? When you differentiate del E to the power of at del t, you get a e a t. Remember these differentiations. Alright, so this is this, and you differentiate twice, you get j omega squared. Okay, and you get j omega squared. And j omega squared, what is j squared? J squared is equal to -1. So -1 and -1 cancel. So finally, the so-called wave equations become like this. Del squared E plus mu omega squared mu epsilon E equal to 0. Or we write it as E del squared E plus K squared E equal to 0. So these are the wave equations that we have. Okay, and these are the wave equations that we are going to use from now on. Now, what are the wave equations so important? Now, the wave equation so important straight away that if this thing is traveling in free space or traveling in air, mu will be equal to mu naught. Okay, epsilon will be equal to epsilon naught. Okay, mu will be equal to mu naught, epsilon will be equal to epsilon naught. Then the velocity of propagation in free space, c now is equal to 1 over square root of mu naught epsilon naught. And if the wave is propagating in a media which is not equal to epsilon naught, mu naught epsilon naught, the velocity of propagation is now equal to this. Equal to 1 over square root of mu epsilon. Okay, because of the wave equations here. Now, intuitively, is it correct? If my wave propagating in free space, the velocity is equal to 3 times 10 to the power 8. This is 3 times 10 to the power 8 approximately meters per second. Now, but if there is a material with either mu r or epsilon r, remember mu r and epsilon r is either equal or greater than 1. If that's the case, the velocity in the media is slower now. Slower now. Intuitively, is it correct? It is correct. Because just imagine, okay, in a denser medium, the speed must be slower. Let's say if you run, okay, Usain Bolt can run 9 seconds per 100 meter, right? But make him to run in a swimming pool. See whether he can run 9 seconds per 100 meter. No, obviously not. The water resistant, the water is so dense. Okay, so it is obvious that, okay, this is intuitively correct that the speed of wave propagating in a denser medium would be slowed by the medium itself. Alright, now what are these equations? Now these equations are these sets of equations, but by substituting this and this. Okay, by substituting this and differentiate. Remember, differentiate one time the j omega comes out. Alright, so this one becomes like this. So the Maxwell equations become like this. Okay, again, derivation not needed. And our wave equations is this. Now, what is this k here? Now, this k is what we so call the propagation constant. So now I can write it now in a fuller form is that this one is now has a E minus J K. Now what is this K here? This K is this K with a unit vector. Now, I'm writing it in very general forms, okay, because the wave, if I propagate this way, it is in the x direction. If I propagate way direction, k direction, z direction, but the wave can propagate in arbitrary directions, right? So it can be an arbitrary vector. So this is a unit vector. I write in a very general form. Now, this is a magnitude k, which is equal to omega times square root of mu epsilon, and this is what we call a phase constant. Okay, so the plane wave. Now, what is the plane wave now? The plane wave is such that when a wave is propagating in these directions, the electric field and magnetic field will be contained within this plane. They are constants over this plane, and they are propagating with constant magnitude but changing phase. Okay. Now, at this point, somebody must want to ask, is it realistic or not? A wave that is infinite in two dimensions and propagate with a constant magnitude in another dimensions. It does not seem to be physically correct, but let me assure you that, okay, it is so-called locally correct. Let's say if I have antenna, I will prove it to you, or we will prove it to you in a higher year that no matter what size or shapes of your antenna, what kind of antenna is it? It's a dipole, it's a monopole, it's a Yagi array, it is whatever it is. When you are far away from the antenna and you take a small patch of your receiver, let's say you construct a receiver here, around this receiver, the incoming wave always appear or behave like a plane wave. So plane wave is not something useless. Okay, just academic. Okay, and concern everywhere. It is true. Okay, it will behave like a plane wave, and it shows that the difference between the antenna problem and the plane wave is that, okay, all the behavior will be exactly the same, but just that the magnitude will be decaying, that's all. Has to decay, right? You know that when you further away, the energy must be lower, otherwise cannot be correct. Okay, that's the only difference. But plane wave is useful. Okay, and this is a wave constant. Now, and one thing I want to point out early at this point here is that this is what we have for engineers, okay, for a wave, forward propagating wave. Forward propagating wave. Alright. But sometimes when you read books, their forward propagating wave is like this. Notice the sign? Plus minus, minus plus. Don't get confused. This is the conventions used by engineers. So if you decide that the conventions are like this for propagating wave, the books is engineering books. This is a convention for the physicists. So you find that they use this kind of conventions. Okay, so this book is written by a physicist, a physics book. Okay, that's all. Okay, the conventions, it just when the phase in the time domain decreases, the phase in frequency in the spatial domain must increase, or the other way around. So compensate off. Never mind. You'll get the same way, but this is the engineering convention. This is the physicist convention. Now, so what is the important things about this K? This K also determine, this magnitude K also determine the wavelength in that particular medium. Okay, K is equal to omega square root of mu epsilon, omega square root of epsilon, which is also equal to 2 pi lambda. Okay, Okay, so now let me rub it off and let me summarize here. C is equal to 1 over square root of mu naught epsilon naught. V is equal to C over square root of mu r epsilon r. K is equal to omega mu epsilon, which is equal to 2 pi over lambda. And lambda is equal to lambda naught mu r epsilon r. Now, because of the material property, because of material property, you can see that not only the speed of wave traveling in the denser medium is lower down, but the wavelength in the denser medium is also smaller, shorter. Okay, same analogy, because just now I said when we run in air, you definitely run faster than in water. Same thing, when you run in air, your steps will be much bigger than when you take in water. Okay, so it's the same thing. Alright, so now these are the things that we have. Okay, so far, that is what the things that we have. Now, in general, electric field will have three components. Okay, electric field will have three components: Ex, Ey, Ez. Okay, electric field will have three components, magnetic field will have three components, right? Okay, so now let's assume that for a simple case, okay, which we only has one component for the electric field, E is equal to Ex, Ax. Now if E is equal to Ex, Ax, I put E equal to Ex, Ax. Now this is my del squared plus K squared, alright? Remember the wave equation is del squared E plus K squared E is equal to 0, or del squared plus K squared E equal to 0. Alright, this is what it is. Okay, del squared plus K squared E equal to 0. Okay, so if that's the case, okay, since this is Ex and this is constant, the rest are all 0, 0. So what we have is now, for the simplest case, we have del squared Ex, del Z squared plus K squared Ez. Z. Now, why del X squared equal to 0, del Y squared equal to 3 is Ex. Ex means E is polarizing in the X directions. Okay, but we say that Ex is the electric field is propagating in the Z directions. Okay, so if now the E here is equal to Ex, a function of Z. Okay, therefore even the electric field will polarize in the X direction, but because it is propagating in the Z direction, the change is in the Z direction. The change is not E and X. Remember, our plane wave means that there's no change in that plane. Okay, so del squared X and del squared Y equal to 0. So only this one. Now this one becomes reduced to a very simple second order differential equations, which you are very familiar with. Second order differential equations of this kind, that means the possible solution for Ex of a function of Z is either this, or this. Remember, this is the combinations of this and this. Okay, the third solution is the combinations of the first two. Alright, so now we have the solution is now, this is my forward propagating wave, backward propagating wave, and this is a combination of both. Alright, forward propagating wave, backward propagating wave, and a combination of both. And once again, a reminder that the velocity is equal to V is equal to omega over K. Okay, V equal to omega over K is equal to C over mu R epsilon R. Now, the mu R is gone. Why the mu R is not here? Because basically, in most of the material that you are concerned with, mu R is equal to 1. Okay, for cable, for concrete, for everything, mu R all equal to 1. Mu R is not equal to 1 only when they are non-magnetic, such as when they are magnetic materials like iron and things like that. Alright, all the rest of the mu R is equal to 1. Now, I just want to finish the solution for magnetic field. I'm not going to go to the general plane wave. I just want to go to the solution for the magnetic field, and then we stop here today and go for the revisions, right? Okay. Now, the solution for the magnetic field is the same thing. Okay. Remember, we have the Maxwell equations. Once we got the electric field, we substitute the electric field inside here. We find the curl of electric field, and there you go. This is my magnetic field. So now, if my electric field now from propagating wave, E is equal to EX, okay, and let's say it has a magnitude, and E minus JK Z here. Now remember there's an EJ omega T here, we never write, alright? There's an EJ omega T here because it's a sinusoid, so we never write the sinusoid. But remember there's an EJ omega T here, and the reason why I never write because del T has already been taken care of, so there's no longer differentiation in respect to T, so it's just implicit, okay, implicit. Alright, so if we put that into the curve, okay, into the curve. Now, since there's only one component, the curve is very easily up. So now my H, okay, is now equal to this one. My H is equal to this one. Alright, so if my H is equal to this, okay, I can find the ratio between my E and H. I find the ratio between my E and H. My ratio between E and H is now giving me square root of mu over epsilon. And for free space, mu equal to mu naught, epsilon equal to epsilon naught is equal to 125, which is equal to 377 ohm. Alright, this is just some illustration on how the plane wave actually can propagate. Now, the electric field will be pointing in one direction. The magnetic field will be pointing in other directions. Did you notice? E is EX, H is HY, HYAY, and the propagation directions is in the Z direction. We say the propagation direction is the Z direction. So for the plane wave, EHZ. EHZ. Remember our XYZ. XYZ. EHK. XYZ EHK. EHK. So now K is in the Z directions. Alright. So the electric field will be pointing in the X direction, oscillating. Magnetic field pointing in the Y direction, oscillating. And the propagation is in the Z directions. Okay, and some animations look like this. Electric field, magnetic field. Okay. Now I don't want to go through this one. Let me just have a quick recap on what we have done. All right, because a lot of equations. we started off from the Maxwell equations. We say that, okay, Maxwell equations theoretically is good to solve for any electromagnetic problems. Alright, but for plane wave propagations, we need to remanipulate the Maxwell equation into some forms that we can find a decent solutions. Okay, you look at this one, you don't know what is the solutions, no point. Alright, so we have to manipulate. So we do some manipulations until we arrive at this form here. Arrive at this form here, we said, well, looks good now. What other simplifications can we do? Now, the first simplification that will come into mind, we say that, okay, what happens if my electric field and magnetic field is sinusoidal, a single frequency? Okay, a single frequency means that my electric field will have this kind of time variations. Okay, and if I have this kind of time variations, I sub in this equation here, electric field and magnetic field the same, alright? They have the same time variation, they must have, alright? So if sub inside here, I will be able to differentiate with respect to the time twice, okay, to get to something over here, okay? And j squared equal to -1, so this will become 1. So this is now become my final wave equations. Now, this becomes my final wave equation. And from this final wave equations there, okay, let me assume that I have a simple case. Because when I say electric field pointing in that direction, it's arbitrary, right? But can I rotate my coordinate system, reorientate myself that electric field is oriented in the next direction? I can. You know, coordinate system can be rotated. So for simplicity, okay, I said my E is equal to EX AX. So my electric field is pointing in the X directions, and assuming that my electric field is propagating in the Z directions, then in that case, I sub them into the wave equations here. Alright. I sub them into wave equations here. I find that del squared, del x squared, and del squared, del y squared are 0 because it is propagating in the Z directions, not x and y. Alright. Then finally, I get a simple second order differential equation like this. And the second order differential equation will have this kind of solutions. So we can say that, well, this is our forward propagating wave, this is our backward propagating wave. And once again, I say that our convention is different from the physicists. And once we get the solutions for the electric field, we can submit back to the Maxwell equations. Okay, after differentiation, this is our magnetic field. Okay, this is our magnetic field. And finally, what are the takeaway now? Finally, what are the takeaways now? My E EX, okay, EX, AX, EJ omega T, E minus J KZ. This is my forward propagating electric field. H. So first thing first, exactly the same. Okay, exactly the same. And the second thing, this is what we call the intrinsic impedance of wave propagations. It's just like your impedance in a circuit. Now, what other things that do we know? We know that K is equal to omega mu epsilon, which is equal to 2 pi over lambda. Now, remember your V is equal to F lambda. Okay, so V is also equal to omega over K. Right? So now we have V is equal to C over square root of epsilon r, and lambda is equal to lambda naught over square root of epsilon r. Right, so these are the final things. Oh, one more thing. My drawing is bad. E cross H. And electric field, magnetic field, and the direction of propagations are in the three orthogonal this what's it called coordinate system. Okay, three orthogonal coordinate system, x, y, z. Okay, if this is my ex, this is my hy, this is my direction of z. So the plane wave is propagating like this with the electric field, x and y and z on one plane and propagating in the direction this way. Now, this is true even if my electric field and magnetic field has more than one component. Why? Because basically right now is x, y, z, right? If it's x, y, z, right? So if I rotate it, it has to still the same. If I, no matter how I rotate, okay, no matter how I point, these three will always be in the orthogonal system. This is now x, y, z. If I rotate it this way, it's still the same, x, y, z. If I point this way, it's still EHK. Okay, if I point that way, it's still EHK. Okay, this one we'll show it to you in our next class when we do general plane wave. Alright, so EH and K will be always like this. And the magnitude of electric field and magnetic field will always be like that, no matter where it points. Okay, no matter which is the direction of propagations, this property will be always true. This property, this property, this property, this property, this property, this property, this property will be always true. Although today we show only for a simple example for E polarized in EX, H polarized in HY. But in general, no matter where they polarize to, okay, where they are pointing to, this will be always true. Okay, so this is where I want to stop today before I do the revisions. Any questions? I know the Maxwell equations and the curve and all this will scare away a lot of people, but once again, I want to emphasize that we are not asking you to derive the wave equations. Okay, and you look at the tutorial, you see that we only want to ask you to make use of the results, okay, to solve more problems. Okay, we are not going to ask you to derive all the wave equations and all those things. It's only the final answer, final solution that we want you to do, or want you to know. Alright, any questions? 6:38. We still have 6 MIA. Okay, do you need 5 minutes breaks before we go and do the revisions? No, 3104C is a prep module. In 3104C, we introduce you to various system components, how to build up the different components that compose of a general RF system. And then we look at the components, what are these components? That means when you want to assemble a system, you want to buy this component, what are the things that are gain or frequency band? Then in the 4 levels, we teach how to precise level 4000 is more but in level 3 is basically just general thing. But level 3 now about 3104C current things. And
the feeling point is very ridiculous. So I don't know whether my point is enough to be
no, we are in fact this year the 3000 module and actually we got the problem. I opened the classroom and now we have 75 we will try there'll be 2 pieces. This is piece 1, and then piece 2 will depend on this transmission. There'll be 1 exam. There'll be 1 exam. We'll come to it. We'll come to it again. All right, ladies and gentlemen, let's do a very quick revision once again. Now, the vector things. Now, what are the things that you really need to know? You need to know are basically elementary length, elementary area, elementary volume. Okay, elementary length, elementary area, elementary 3 volumes. Elementary length is very simple. If it's xyz component, it will be dx, dy, dz. And the vector is dxax, dyay, dz. Now, whether it's plus and minus, okay, whether it's plus or minus, whether it should I take plus dxax or minus dxax, okay, we'll come to it again, alright? Okay, so it's very simple. For area, 2 length and 1 vector, which is also very simple. If my dx, dy, the vector must be dz. dx, dz, the vector must be ay. dy, dz, the vector must be ax. So it is very simple. The 3 must be orthogonal. You cannot repeat. Okay, you cannot have dx, dy, ay, which is wrong. Okay, so the 3 must be perpendicular. Now, whether it's plus or minus, you got to look at how the contour goes. Let's say if this is the area and this is your contour, dx, dy, this is x, this is y, okay, and this is your contour, then x, y, z, this is plus az. Now, but if this is your integration contour, if it's like this, then it's dx, dy minus az, because if it's contour like this, the vector point in. Alright, so you just look at which direction does that go. Same thing for all the rest. Alright, same thing for all the rest. Volume is no problem. Just simply volume. 3 length. Okay, just simply 3 lengths. Now, when it comes to cylindrical and spherical, remember length. Okay, not angle. So when you have d rho, dz, you cannot have just d phi. You must have rho d phi. Okay, it's just length. Okay, must have length. Same thing down here. dr, you cannot just have d theta and d phi. You must have r d theta, rho d phi, or r sine theta d phi. Alright, and same thing. Okay, when it is length, it is in the same direction. dr, ar, r d theta, a theta, rho d phi, a phi. Okay, in the same direction. But when it is area, it is again the third directions. Okay, it is the third directions. Now, the next thing is that, okay, remember your vector, where's the vector products? Okay, your vector products. There are 2 kinds of vector products. One is dot products. When it's dot products, it means that it's A times B cosine of the angle between them and become a scalar. Okay, when it's the cross product, the result is A times B times sine of the angle between them and resulting in another vector. Always your right hand rule. Okay, x, y, z, a, b, n, a, b, n. Okay, a, b, n. Alright, it's always like that. The starting vector, the end vector, the resultant vector. Now, then what is always tested is not the derivations. Once again, we will not ask you go and derive divergence theorem, Stokes theorems. We have gradients, we have divergence, we have curve. We will not ask you to go and derive all these theorems. Okay, but basically you will be tested on something like this. Okay, how to verify divergence theorem and how to verify Stokes theorem. Now, verify divergence theorems or verify Gauss law, something similar. Okay, what does it involve? It involves divergence theorem if it's involved. Okay, it involves an integration, a surface integral. Okay, and a volume integral. A surface integral and a volume integral. Now surface integral, once again, you have to know the elementary surface area. Okay, you have to know the elementary surface area. And you have to know which the directions, the vector, the area vector. Now, then the dot products. The next thing is that sometimes the vector and the coordinate systems are not even in the same coordinate system. One might be in a rectangular coordinate system, one might be in the cylindrical coordinate system, one like this. So when you do dot product, you must be careful, okay? And my advice is always look at, if it's a surface, look at the surface. Or if it's a contour, look at the contour. And you convert everything to the surface or to the contour before you do the dot product. Let's say if this D is not given in this form, if you begin the XYZ coordinate system, you just convert it into your spherical coordinate system before you do the dot product. Alright, so once you that, it's quite straightforward. Alright, it's quite straightforward. Main thing is that make sure that you know where is your elementary volume, elementary length, elementary area, elementary volume. Now, okay. This one contain a good questions here. Just now we say that, well, okay, my elementary length, should it dx ax or what should I do? Now in these questions here, you can see that if I integrating from 0, P1, P2. I'm integrating from 0 to P1. My dl is equal to dx ax. No problem, right? Now, from P1 to P2, my dl is equal to rho d5 a5. No problem, right? Now, this is 0 to P1, P1, P2. From P2 to 0, what is my dl? What is my dl? Should I put it as dy ay, or should I put it as minus dy ay? Because this is integrating from here to here. What should I do? Is it dy ay or minus dy ay? Now, the answer is, okay, the answer is very simple. P20, if your dl is put it as dy ay, then your integrations, because this is 0, this is 3, y equals 0 to 3. If you put it dy ay, then you integrate it from 0, 3 to 0. Then you have your fy dot dy ay. If you put it as dl is equal to minus dy ay, that means you already taken care of the negative directions already. Then your integration becomes 0, 3 fy dot minus dy ay. You can see these two are the same, right? Because the negative sign, you can switch the directions of integration. Correct or not? Remember, you have 0 0 to 1 minus dx is equal to 1, 0 dx. Alright now? So you can either take care of the directions and just do this, or you just do a universal one. Okay? Now, for those of you who are worried about confusions, because sometimes you don't know which direction it does point, my advice is use these general forms and take care of it using the from point. Just follow the point. Okay, so you don't get confused. You can use a general form. Okay, but if you can follow, then it is all right. All right. If not, do a general one. All right. Is there any questions? Any questions? Okay. Once again. Okay. For these chapters. Okay. This chapter there will be one question. All right. There will be 4 questions in the quiz. 1 question coming from this chapter. 2 questions coming from the electric field chapter, and 1 question coming from the magnetic field chapter. Alright, so all the 3 chapters will be tested. This chapter, the important thing is basically you got to know the difference between the dot product and the cross product, dot product and cross product. Okay, how to do all the divergence and curve. Okay, how to do the divergence and curve, and of course the important things that know where the elementary length, elementary volume, elementary surface area are. Okay, and remember the vector directions. The vector directions will be very important because, like for instance, okay, when you do this one, the vector direction of course is this one. This is up, that is down, right? Okay, when integrating over this surface, the vector direction is up. Integrating over this surface, the vector direction is down. Okay, integrating over this surface, the vector direction is outside, outward. Now, when you do this one, for instance, the vector direction is outward, but down below this vector direction, what is this vector direction? This vector direction, you can say that is equal to minus AZ, but minus AZ, how to do all the dot product? Remember this vector direction, it is A theta as well, A theta, A theta. Remember, this is my A theta, so it comes to here, it is also A theta, or U theta. Alright, so you got to be sure about the vector directions. And that's about all for this one. Okay, be sure of the vector directions, and be sure where the vectors are pointing. That's all. Okay, so this is 1 question done. Now for electric field, very simply, electric field is actually force per unit charge. Okay, so electric field is a vector. E equal to Q over 4 pi epsilon R squared when you're pointing in the right direction. Okay, and we say that, well, electric field, what are we going to do with electric field? If there is not, instead of single discrete charge, we have a charge distribution. We say no problem. We just take the elementary, once again, elementary length or elementary area or elementary volume, take the electric field, and then we sum them all. So it's again integration problem. Now then we say D equal to epsilon ER. Then we have Gauss law. Okay, when we say Gauss law, remember we say that Gauss law, we always try to find a Gaussian surface which the left hand side can drop out very easily. So we have 3 scenarios here which you always encounter. It is not likely that you will encounter anything outside these 3 scenarios. Okay, these 3 coordinate systems, You have 13 coordinate system, you only learn 3. Now we will be tested on the other plane, not to worry. Okay? You either this, or this. So this one, E dot dA is just equal to EA. For the other one, what is the E dot dA? Normally what you have is the electric field always pointing out this way. The electric field will not cross here. Alright? Same thing, the electric field only cross here, right? The electric field will not cross the other side. But if you put a box here, it's a different story. Okay, hang on. There is a variation. Does not mean that this thing will come up in the quiz, okay? I don't know, but not likely lah, huh? Because this one, the charge is here, right? The charge is here. So the electric field is constant, so you draw a box like this. What happens if I have a charge density here? Then you may have to draw a box like this. I don't know also. But then you have electric field going to both sides. Correct or not? But there's no electric field coming from the other four sides. Okay, it can be another distant scenario. Maybe we'll do it next year. Next year. That's coming.
So I think you count your question, everybody just leave blank.
Sorry? No, next year. Next year. It's too late for this year already. Okay, so this one will be. This one will be what? This one will become ER times 2 pi RL, right? Drop it like this. And this one will drop it. This one, how will it drop? This one become ER 4 pi R squared. So it is very straightforward. Now, the tricks, the so-called trick comes from this side. How to evaluate the charge Q? How to evaluate the charge Q? Okay, the charge Q, how to evaluate the charge Q? The charge Q, it depends again, just like I said, if it's a constant, you just multiply. If it's not constant, let's say in this case here, it's not constant, how? Now, for those of you who can see the tricks, you must know how to do the shells multiplied by area, small area, and all this. But if you cannot, again, my advice is always equal to this way, rho dV. You put the charge density inside there, and you simply put the charge density, which is a function of whatever it is. Normally it's function of R only. Cannot be a function of theta and phi, because why? If there's a function of theta and phi, the electric field will not be radially outward anymore. So it's only a function of R. So we just have R squared sine theta d theta d phi dr and integrate. That's all. Okay, and integrate, that's all. Now, if you are smart, you don't have to write this. You can do all the shells thing and all this thing. But if you are not, you put in there and integrate. You can never get it wrong. R equal to A to B, depending on where you want to be. Theta equal to 0 to pi, and phi equal to 0 to 2 pi. You always got it right. Alright? So, not to worry. Okay, even you don't know how to see the shells and all these things. Okay. Okay, then we have potential. Now, I have a few questions. People still do not know about this potential thing. V equal to minus grad V. V equal to minus V dot dl. Now, there are still few questions of why this minus thing comes about. Now, what is grad V? Grad V is equal to del V, del T, del V, del X, AX, plus del V, del Y, AY, plus del V, del Z, AZ, right? Excuse me. Disgusting. a simple situations. Okay, let's assume that this thing is not here. Del V del X EX. And what does it mean? Means that if I'm in the X directions, my V is increasing, right? Let's say this is equal to 10. That means when it is 1, it is 1. When 2, sorry, 1 it is the radius 10. How to draw the radius 10? This is 10, right? Okay, so this is 11. Am I correct? So the radius is 10. Am I correct? So that means the potential is increasing in the X directions, right? But the electric field is pointing from the high potential to the low potential. Remember, the conventions of electric field is pointing from the high potential to your low potential. If the positive charge, this at infinity is 0 potential. So from the high potential pointing to low potential. So you can see that this is, if this is positive, this is AX, you need a negative down here. You need this negative to point it back. Okay. So if the dV dx is positive, the electric field must be negative in X directions. Can you see that? No, am I confusing you? I'm confusing you, is it? Yes, sir. Okay, one more time. If I'm confusing you. Okay, for a simple case, dV dx AX. This is my gradient of V. Now, let's say if this is positive 10, it is 10 AX. Now, if without the minus sign, then E will be equal to 10 AX. That means E will be pointing in the AX directions, which is not correct because potential is increasing. Potential is increasing in the X direction. At this point, it is higher potential than this point, right? That's what is increasing means. Higher at this point is mean. But we know that our electric field is from high potential to low potential. Okay, that's why it is plus minus. It is high potential to low potential. So electric field must be pointing in that direction and not this directions. And that's why you need this negative sign here, so that electric field is pointing in the other directions. Alright. Same as this one here. Now, and this one here that raises another problem is that, okay, let's see why is this negative sign first. Okay, let's look at this one here. This is plus, this is minus or 0. This is the electric field E. This is Y directions. So E is equal to minus EY AY, right? dl is equal to dy ay, right? So integral of E dot dl is equal to integral of minus ey dy. Let's say from 0 to 10. Now, isn't it ended up with a negative potential? If we integrate from here to there, 0 to 10, negative potential, which is not correct. Then you must have a negative sign up here to account for that one. Otherwise, it's wrong again. Okay, so this negative sign is there to get the conventions. Now, that raises another question is that, okay, what happens if this is like this? Electric field is like this. So you got like this, you got like this, you integrate like this. So you ended up getting a negative value. Okay, you end up negative. Is there anything wrong? If this is the problem, this is 10 volt. Oh, sorry, this is 10 volt. This is 0. So this is integrating from whatever, y. Don't say like this is b. This is 0. Okay, so this is y equal to 0. Y equal to 10. Okay, integrating. Now you ended up with a negative value. Is there anything wrong? Nothing wrong. Okay, nothing wrong, because basically when you're integrating from here to here, you are making the assumptions that the potential at this point is lower than the potential at that point. Okay, if you're integrating from, this is the first integrating point, the second integrating point, integrating from y equal to 0 to y equal to 10, you are assuming that y equal to 0, it has a lower potential at this point. But actually, this point is a higher potential, and that's the reason why it turned out that the value V become negative. Alright? So nothing wrong. If you find that your value of potential become a negative, that means that when you're assuming that the first starting to end point, you're assuming that the starting point is lower than end point, which is wrong. Just that this is has a higher potential than the other. Okay, that case comes from this one. Somebody asked me, why the integrations, okay, to get the potential, they integrate from B to A instead of A to B. Because we know that B and B here is a lower potential than A. So we're integrating from B to A, we get that positive value. But if you integrate from A to B, it is nothing wrong. All you get is a negative value, that's all. That means that shows that, okay, when integrating from A to B, you get a negative value. It just shows that you are initially assuming that A is at lower potential is wrong. A is at a higher potential, that's all. Okay? And that brings another question is that, if that is the case, how am I going to find the capacitance? Because C equal to Q over V. Now my potential is negative. Oh, capacitance is not defined that way. Capacitance is the capacitance of a capacitor, whether it is plus and minus or it is plus or minus, they have the same capacitance. Whether you turn this way around or that way around, it's not the same. So all you have to do is just take the absolute value of V, you still get the capacitance. Alright, so don't have to worry that if you do this integration, you get, how can I get a negative value? Because you get P1 to P2, potential is actually potential difference. Okay, so that means the difference is not, initially you say that this 1 is lower than 2, actually it's wrong. It's 1 is higher than 2, that's not all. Okay, and you can find the capacitor, no problem, just take away the negative sign. Alright, so that is about the potential. Now, and we say that, okay, what are the things that we most do on that one beside the Gauss law? Okay, beside the Gauss law, the most of the time what we do is capacitance and resistance. Capacitance and resistance. And what do we do to find capacitance? Assume a charge density. Charge density go to Q, remember? And the charge density get to E using Gauss law. And E got to V, V equal to minus E dot dl. Or the other way, if they give you V instead, then you can get it back. V equal to minus grad V as well. Okay? And then you see Gauss law, and this one you back. Same thing, if you, for resistance, This is capacitance C equal to QP. For resistance, you always have a current density, and current density just give you I. By integrating, you get I. And current density, you get to E by J equal to sigma E. Now this sigma and this sigma are not the same. This is charge density, this is conductivity. Okay, once again, charge density, conductivity. And this E is once again here to V. The same thing. So R is equal to V over I. Alright, so this is the couple of most important questions always comes up with that Alright. Okay, finally, magnetic field. Magnetic field once again, magnetic field's discovery is from magnetic force. Okay, F equal to Q U cross B. Okay, X, Y, Z, right hand rule. Everything is right hand rule, X, Y, Z, X, Y, Z. E, H, K, right, X, Y, Z, no, right hand rule. Now, what are the important things? Ampere's law. Okay, Ampere's law, when there is a long straight wire, always use Ampere's law. Or when you have a long solenoid, always use Ampere's law. And Ampere's law is much more easier to evaluate than Bart-Sabat's law. So if you can use Ampere's law, don't do Bart-Sabat's law. Okay, this is Ampere's law. Ampere's law B dot ds is equal to I. Okay, and once again, when we apply Ampere's law, because of long straight wire, because of symmetry, this side always drop out to become B times 2 pi r. Okay, B times 2 pi r. And remember, the B direction is always in the 5 directions. Okay, in A5 directions. Alright, in the A5 direction, in the circumferential direction. Alright? Now, okay, Bart-Sabat's law. Now, Bart-Sabat's law, what are the things that you need to be careful of? Not only in CA, but also in exam. Bart-Sabat's law, the important thing is write down these 3 components clearly. Once you write it down clearly, you know where it is. Where is ds? ds is the elementary length in the directions of the current flow. Elementary length in the direction of current flow. R double prime is the distance between this elementary length and the point of interest. Okay, this is R double prime. UR double prime is the unit vector of this thing. Now, how to see that this one dz cross AR double prime becomes A5? How to see that?
What they call the sine thing.
Now, if we look at this one very easily, this is here. Okay, this is here. Now, this vector has 2 components, right? One component is here, one component is here. Am I correct? Now, this component is the same as AZ. So the cross product is 0. Correct? Now, this guy got 2 components. One component is here, but this one cross this one is 0 because the 2 vector in the same direction is 0. So only this vector cross this vector will get a value. Correct or not? Okay, only this vector. So you have a AZ here, UR double prime here. I got these two components. Okay, I can get it into these two components. Now this one cross this one equal to 0. Now what is this component down here? What is this component? What is this component? If the cylindrical coordinate is your A rho. Remember? If it's pointing like this, it's an R. The projections onto the XY plane is the rho component. Remember, we said many times before, if this is R, the projection is rho. Alright? Rho component. Now, so if you have Z, you have rho, what is the resultant component? Cylindrical coordinate system. Remember your cylindrical coordinate system? Rho phi Z. Rho cross phi give you Z. Phi cross Z give you rho. Z cross rho give you phi. Right? Rho cross Z give rho cross phi give you Z. Phi cross Z give you rho. Z cross rho give you phi. So Z cross rho give you phi. So this one ended up A5 dimensions. Alright? Or if you look at it this way, same thing lah. This guy here, Z is here, UR is here, of course it's there. Okay. But if you cannot see, you will resolve into like this cylindrical coordinate system. Alright. Okay. So remember, okay, and okay, this one is actually the end of it already. Is when you do mutual or self-inductance. What we do inductance, same thing. What do we do? How do we do inductance? We have A, J, okay, which is give you I. J or I will give you, if I use the Ampere's law, okay, I have a B or H. I get B or H. This is my Ampere's law. And B of H give me what? B of H give me 5. Because 5 is equal to integral of B dot dA. Alright, so finally my inductance L or M is equal to 5 over I. Alright, so same thing. Let's say from this one here, I got my B5. I get my B5. If my B5, I integrate my B5, I get the flux. I get the flux, I get the inductance. So I can even find the inductance of this particular example if I want to. Although we didn't find inductance. And if you want to find the inductance, self-inductance of these two examples, remember there are two components. One component is inside and one component outside. So you have to integrate from here to here and then there. Alright, one final thing about magnetic field is your Faraday's law. Okay, Faraday's law, remember Faraday's law, EMF is equal to minus del phi del T, but phi is equal to B dot dA, and B dot dA has two components, okay, two components, each component can change, okay, and remember, flux linkage. What do you mean flux linkage? Flux linkage means there must be magnetic field crossing the area. Alright, just like Gauss' law, okay? The flux electric field must cross. Magnetic field here also must cross. That's flux. If the electric field just pass through, parallel to the surface, it's not flux. Okay, it does not, no flux working. Same thing if the magnetic field just passed like this, there is also no flux. So whether the V is changing or not, it does not care. Okay, it may be the magnetic field keep changing in this direction, but it is a parallel. It also no flux. All right, so have to be sure of what they mean flux. Flux means the magnetic field must be crossing. All right, and I think that's about all. Okay. Right. Have a quick one. This one supposed to be last week one already. And this Friday is a quiz. Next Tuesday we will finish the chapter on the plane wave propagations and then do the tutorial as well. Okay. This current is coming out, this current is going in. Alright, the convention is this current is coming out, this current is going in.
So the going in is minus.
No, the dot means coming out. This is an arrow.
Then the negative I,
The cross is going in.
so the
Alright,
negative,
don't care about this one, don't care about this one, okay. Don't care about this one. You might get confused, alright. Okay. Okay, so one current is going out, one current is going in. Okay, that's all.
是minus，动是 minus。Left side 是 going in，right side 可以coming out啊。Fuck you! This one's coming out. I think it's A. It's cover cross. One is up, one is down. Show me right. White. 搞得痛了，搞得痛了。Lisa, bro, Lisa, and Lisa the other way, like a
One card is going out.
Dạ là, thì số hiệu cô này hả? Đúng rồi, this way. So get my point. One go this way, the other go the other way. Bây giờ measure here. Let me repeat like that, okay? So you can see my one going this way, going the other way, Friday no two hands, bro. Friday only got one hand. Now I can lend you, right? Friday I can't lend you.
Alright, can we close shop earlier? Finish? I got a class at 6.